have been trying to get Steven Weinberg to the festival for a number of years, and it's a big trip from Austin to come to New York for the festival, so we needed to do something special. And we thought about it, and we realized that, as many of you know, the typical program at the World Science Festival is one in which we have a number of people, leading scientists, leading thinkers, artists on stage discussing various topics at the forefront of ideas, forefront of science. But we have never had a program where a single individual takes a stage and speaks about something that they consider of vital importance. So we decided to inaugurate a new lecture series. So once each festival, we're going to have a preeminent scientist who will come and speak on something that they consider critical for the general public to have some insight into. And it is our great pleasure that the inaugural lecture is indeed going to be given by Steven Weinberg. So as many of you, yes, please. So, as many of you know, Steven Weinberg is the Josie Welch Professor of Science at the University of Texas, Austin. He's a member of the Physics and Astronomy departments, numerous awards, accolades, National Medal of Science, and of course, the Nobel Prize in Physics in 1979, which was awarded for his insights, which basically took the first major step toward what Einstein called the unified theory, a theory that would perhaps describe all of nature's forces in one single package. The previous step was taken by Maxwell in the late 1800s. Steven Weinberg, who shared the prize with Salam and Glashow, took the next step, giving us the electroweak theory, for which he was awarded the Nobel Prize. Now, all of that, I think, is well known to you, and I think it captures well the stature of the individual who will be addressing us here this afternoon. But I worked at IBM as a summer student in the 1980s, sort of to make money for college kind of thing. And the person who I worked for there, his name was John Koch, an eminent computer scientist. And when I, a couple of years later, told him that I was invited to give a talk at UT Austin on some work that I'd done in string theory and that Steven Weinberg would be there, he took me to the side and he said, "You should know there are Nobel laureates and then there are Nobel laureates." Steven Weinberg is a Nobel laureate. And indeed, he is the preeminent theoretical physicist in the world today, and it gives me a great pleasure, a great honor to give you now Professor Steven Weinberg.
Thanks, Brian. Welcome. Thank you, Brian. I feel very honored to inaugurate what I think will be a great series of lectures under the heading of On the Shoulders of Giants in this wonderful festival in years to come. I also feel very honored that you showed up here on such a beautiful day when it would be so nice to be outside and sit and play a game of chess or something in Washington Square. So thank you. It is, this year we are celebrating, we in physics are celebrating an anniversary. It is just 100 years since Ernest Rutherford, in his laboratory at the University of Manchester, announced the discovery of the nucleus of the atom. In the experiment in his laboratory, a beam of charged particles called alpha particles that are produced by the natural radioactivity of radium was allowed to fall on a very thin gold foil. And to Rutherford's great surprise, it was found that some of these alpha particles were bouncing backwards. And Rutherford concluded from this that the alpha particles must be encountering something inside the gold atom, something very small and very heavy, having most of the mass of the atom. And this he identified as the nucleus of the atom. It was the beginning of modern atomic and nuclear physics. Now, this was great science, unquestionably, but it wasn't what I would call big science. Rutherford's experimental team consisted of one postdoc named Geiger, you may know the name, and an undergraduate, and that was it. He was supported by a grant from the Royal Society of London of £70. It's true money was worth more then, but still £70. The most expensive part of his experimental setup was the sample of radium. Radium was then very expensive, but he didn't have to pay for it. He borrowed it from the Austrian Academy of Sciences. But experimental science soon got much bigger. The alpha particles, these energetic charged particles from radium decay, didn't have enough energy to actually get inside the nucleus of the gold atom. The repulsive force was too great. They couldn't break through that electrical repulsion. In order to break into the nucleus and see what it's made of, it was necessary to use particles, whether alpha particles or other charged particles, that were not coming from natural radioactivity, but were artificially accelerated to higher energy. And in the 1930s, a variety of accelerators were invented for this purpose. First, perhaps the most famous, is the cyclotron, invented by Lawrence. And they got bigger. Maurice Goldhaber, who for many years was director of Brookhaven Laboratory and alas died a few weeks ago, once recalled that he had seen a photo of Rutherford sitting with his apparatus in his lap. And then he saw a later photograph of a number of nuclear physicists sitting in the lap of a cyclotron. This work in building accelerators was taken up again after World War II, and now with a new purpose. The work continued on studying the nucleus using particles to get inside and break it up and see what's going on there. But now there was a new purpose to create new forms of matter. This had already started in the 30s with the discovery of a variety of new particles that don't exist in everyday life that were found in cosmic rays. Cosmic rays are extremely energetic charged particles that strike the Earth from outer space and produce reactions in the upper atmosphere in which new forms of matter are created. The cosmic rays themselves are nothing special. They're nuclei of various atoms, hydrogen, helium, and so on. But they have so much energy that when they hit oxygen and nitrogen atoms in the upper atmosphere, they produce new things. The first of these new things was called the positron. It's the antiparticle of the electron, a particle just the same as an electron, but with positive rather than negative charge. And then other particles were discovered. I needn't burden you with them, called mesons and hyperons, about a dozen or so new particles. And when I was a graduate student in the 1950s, I had to learn a lot about cosmic ray physics because that's where all the information was coming from about new particles. And I remember how surprised I was when a professor at Princeton, where I was a student, Arthur Whiteman, told me that pretty soon physicists would no longer be worried about cosmic rays. They would be getting the information about particles from new kinds of accelerators, which would accelerate known particles like protons, which are the nuclei of hydrogen atoms, or alpha particles, to very high energy where they would collide with each other or with stationary targets, and in that collision, new matter would be formed. I'm going to mention just one equation in this talk, but it's an equation I think you've all heard, E equals mc squared. The energy E required when you have a collision of a number of particles, the energy you have to have in that collision to produce a new kind of particle with a mass m is the mass m times the square of the speed of light. And the bigger the mass, the more energy you need. Now, the reason for switching from cosmic rays to artificial accelerators is not that cosmic rays didn't have enough energy. They have plenty of energy, but they're unpredictable. You never know when a cosmic ray is going to hit your apparatus or hit an atom in the upper atmosphere and do something interesting. Whereas with an accelerator, you know exactly what particles are hitting your apparatus and when they're coming in, and you can do controlled experiments. But for this purpose, accelerators had to get even bigger. The way that the accelerator accelerates the particles is the particles are sent around a ring, and every time they go round, a little extra energy is given to them until they get up to the energy you want. Now, they're kept going around the ring by strong magnetic fields, in which the charged particles' paths are curved. But there's a limit to how strong you can make magnets. And so in order to accelerate particles to very high energy, you have to reduce the curvature of their path. So it doesn't need such a strong magnetic field to keep curving them. And that means you have to make the path bigger. And they did get bigger. When I went out to Berkeley in the late 1950s, Berkeley had what was then, when it was built, the largest accelerator in the world. It was called the Bevatron, and it occupied the whole of a large building up there in the Berkeley Hills where the radiation laboratory was. It was built specifically to create a particular new particle called the antiproton, the antiparticle of the proton, which is the nucleus of the simplest element, hydrogen. And sure enough, the antiproton was discovered as on schedule, but no surprise. But what wasn't expected was that a whole slew, in fact, hundreds of new particles were discovered. So many that theorists began to wonder, do we really even know what we mean by an elementary particle if there are hundreds or 1,000 of them? How could they be elementary? It was a very confusing time, but also a very exciting time. And I remember, though, that a little bit later, an atmosphere of gloom, settled on Berkeley when they realized that to go up to even higher energy, the next generation of accelerators would be much too large to fit into the Berkeley Hills. The next generation were accelerators being built at Stanford and Fermilab outside Chicago and CERN in Europe. They couldn't fit into Berkeley. And they got pretty big. The large accelerator at Fermilab is a ring 4 miles in circumference, no longer something that can fit into a building, but rather a feature of the landscape, which you can see from space. And in this ring, reproducing the Illinois prairie as it was before Europeans came, they have a herd of bison grazing. Right now, we're waiting for new results from an even bigger accelerator in Europe called the Large Hadron Collider. Now, I should explain that the purpose of building bigger and bigger accelerators is not really ultimately to collect new kinds of particle and list them in an album as if you're collecting stamps or orchids. The purpose is by creating kinds of matter which, because they're heavy and unstable, don't exist in ordinary matter, you're filling out the picture of the way nature is, and you're being led toward a set of laws of nature, physical principles that govern why everything is the way it is. In other words, what we were after in building these large accelerators was not particles, but principles. By the mid-1970s, this theoretical progress had been made, quite a lot. We had developed what is called now the standard model of elementary particles. It's a theory that works. It describes virtually all the particles in nature and virtually all the forces in nature, certainly everything we can study in existing accelerator laboratories, has been thoroughly well tested. But it's certainly not the end of the story. For one thing, in the standard model, there is a somewhat mysterious list of particles that appear in this theory as elementary particles. Among them are quarks. Two kinds of quarks. The lightest ones make up the protons and neutrons, which in turn make up atomic nuclei. 3 quarks in each proton or each neutron. But there are altogether 6 types of quarks. The other 4 are heavy and unstable. They're all equally important as far as the standard model is concerned. It's just an accident that 2 of them are the ones that appear in ordinary matter. There are other particles. There's the electron, and it has a couple of siblings, which are just like the electron, but heavier and also unstable. Now, we have a table based on experimental data of the properties of these particles, their masses especially. And we know what their masses are, but we don't know why they are. We've been looking at this table of experimental information about these masses now for several decades with the feeling that it's got to be telling us something, and we don't know what it's telling us. It's a little bit like having a manuscript in a, say, linear A, a language that hasn't been deciphered. You feel you ought to know what it's saying, but you don't know what it's saying. Another thing, astronomers tell us that 5/6 of the matter of the universe is some kind of dark matter, which was discussed already in a panel in this festival. This dark matter, none of the particles of the standard model have the right properties to make up the dark matter. So 5/6 of the mass of the universe is not in the form of anything described by the standard model. Well, it's something we ought to know more about. And finally, there's a little technical detail that gravity doesn't fit in the standard model. It's also something we would like to know more about. So we have to hope for more insight from the next generation of experiments at big accelerators, like the one that I mentioned before at the Large Hadron Collider in Europe. Now that is pretty big. It's 17 miles in circumference. It's not visible from space because it's buried in a tunnel which goes across the border between France and Switzerland. In this accelerator, 2 beams of protons are going round and round, kept in their orbits by powerful magnets. The magnets have a strength, roughly 10,000 times the strength of the Earth's magnetic field, which acts on compass needles. When the Large Hadron Collider gets up to its final design capability, it will accelerate particles to an energy which is about 7,000 times the energy contained in the mass of a hydrogen atom. It's an energy which is about 1,000,000 times the energy of the alpha particles in Rutherford's famous experiment. It is certainly big science. It's also big science in another sense, a human sense, which is not so good. One experimental team at the Large Hadron Collider that I happened to look up for this talk, the ATLAS collaboration, has over 1,000 PhD physicists working together. They'll all sign the research articles when they come out. The title page will be much larger than the rest of the article. And I don't know how a young experimental physicist can make a name for himself or herself working in a collaboration like this. Also, the experiments from planning to completion take over a decade, which is a fair fraction of a scientist's working career. And it may be an experiment which turns out to yield nothing exciting. So I just thank heavens every day that I'm a theorist. I don't have to do that. But we're forced into the mold of big science by the logic of the subject. At any one moment, the particles that we know about are those that have a low enough mass so that they can be created at existing accelerators. And if you want to find new forms of matter to fill out our picture of the way the world is governed, then you have to have higher energy. And we can't help it. The purpose is not to get records for the number of particles or the energy. It's to learn about the laws of nature. Now, there's one particle in particular that we expect without certainty to be produced at the Large Hadron Collider. It's a particle called the Higgs Boson. It is predicted as a necessary feature of nature by a theory that unifies the weak and electromagnetic forces that Brian mentioned in his kind introduction. In this theory, I should explain, the weak nuclear forces are forces that act inside the atomic nucleus, allowing neutrons to turn into protons or protons to turn into neutrons. They're very short range, and hence they only act inside the nucleus. The electromagnetic forces you all know about, that light that's staring me in the eyes, is an electromagnetic wave, and we've all felt the force of magnets pulling on a piece of iron. They seem very different, but in the equations of the theory, they are treated the same way. Also, in the equations of the Standard Model, the particles that I mentioned earlier, the quarks and the electrons and so on, have zero mass. Yet obviously that's not the way nature is. What you have is a situation where you have equations with certain very great simplicity, a great degree of symmetry, a symmetry between the weak and electromagnetic forces, for instance, a simplicity that says all the masses are zero, and yet that's not realized in the solutions of the equations, which describe what actually we see in nature. How does the solutions not respect the symmetry of the equations? Well, there are various ideas. The simplest idea, which appeared in the original version of this theory, invokes a new set of fields in addition to the electromagnetic field and all the other fields of the Standard Model, a new set of fields which pervade the universe, one of which would be manifested as an actual physical particle, electrically neutral, heavy, unstable, which has come to be called the Higgs boson. And this particle, if it exists, will be found at the Large Hadron Collider, because we know enough about it to know that its properties make it findable. It may not exist. There are alternative theories. There's a theory called technicolor theory, which dispenses with these fields and does not predict the Higgs boson, but predicts instead a whole slew of other particles, one of which may recently have been seen at Fermilab, although it's too early to tell, a particle called a technopion. And we don't know what the LHC is going to find. If we did know, we wouldn't have to build it. But we do know, as actually a mathematical theorem, based on what we've already learned, that either one or the other of these new kinds of particles will be found at the Large Hadron Collider. It will settle the question of how particles get masses and how the symmetries get broken. Now, but I would guess that experiments at the Large Hadron Collider are not going to take us all the way to what we want. What we want is a set of fundamental principles of great simplicity, of compelling quality, which will tell us why the world is the way it is. And I don't think we're going to get there from just what we learn at the Large Hadron Collider. So inevitably, physicists are going to be going back to governments and asking again for money to build the next large accelerator, which most of us think would probably be an accelerator which, instead of accelerating protons round and round a ring, will accelerate electrons and their antiparticles, positrons, in a straight line so that they collide with each other, and all the energy in the head-on collision is available for producing new forms of matter. Because you can do precise experiments with this kind of accelerator that you can't do with the Large Hadron Collider. But it's going to be a tough sell. And I'm worried about whether or not we're going to succeed. In fact, I'm worried that this heroic period of first breaking into the nucleus and then creating new forms of matter and developing a standard model, I'm worried that this is going to come to an end in our lifetime. Well, maybe your lifetime. And my pessimism comes partly from my experience with another large accelerator project which was canceled by a vote in the House of Representatives in 1993. This was an accelerator called the Superconducting Supercollider, and I'm going to abbreviate that to SSC. The SSC would have been even bigger than the Large Hadron Collider, a 53-mile circumference, and it would have accelerated particles to 3 times the energy that can be reached at the LHC. And it would already have answered these questions that we're hoping to see answered by the LHC. We struggled to get it funded. About $1 billion was spent on it, and then it was killed, as I said, by a vote in the House of Representatives. One thing I learned during the fight to get the SSC built was that no scientific discovery is remotely as important to a legislator as the economic interests of his or her own constituents. And this is not something evil. This is the way democracy is supposed to work. Legislators are supposed to represent the interests of their constituents. The problem is that it all too often turns out to be the short-term interests, and they don't provide enough wisdom and guidance so that their constituents will respond to the long-term needs, not only of their own little district, but of society in general. An accelerator, a big scientific laboratory, in fact, of any kind, is, among other things, a public works program, which provides jobs for local people and provides purchasing of local products. And generally speaking, the legislator from any district where a big project like this is going to be located will be enthusiastic about it, and every other legislator will look at it with either indifference or hostility. I remember that when I was testifying in favor of the SSC, before the site was chosen, the site chosen was in Texas, before that site was chosen, a senator responded to something I had said and said, "You realize, young man, that right now there are 100 senators in favor of this project. But once the site is chosen, that number will drop to 2. And he wasn't far wrong. For an example, actually referring to the House rather than the Senate, at one point there was a member of the House of Representatives, now retired, Sherwood Boehlert, from upstate New York, who was an enthusiastic supporter of the SSC. And there was a site in upstate New York that was one of the candidate sites for the location of the SSC. It was a bizarre site. It was in the Adirondack Mountains, so isolated that the nearest large airport was Montreal. And, but very early in the process, this site was dropped and was clear it would not be on the short list of candidate sites that would go to the Secretary of Energy. And Boehlert then turned 180 degrees and became an active and very effective opponent of the SSC project. When the site was announced as a Texas site, many politicians and journalists began to call it a Texas pork project. It really wasn't. I was on the site selection committee, and we operated in an entirely non-political way and identified two sites that we thought were the best sites in the country. One of them was a Texas site. The other was a site in Illinois near Fermilab. They both had advantages. The Texas site won, I think, because it had better geology and more enthusiastic support from the local inhabitants. But you couldn't contradict the press, who kept calling it Texas pork. One congressman from the district where it was to be built, Joe Barton, who's still an influential member of the House of Representatives, was an enthusiastic supporter of the SSC. And then when a vote in Congress killed it, he turned against not only the particle physics, but physics in general, I think. And he tried to prevent the funding of American participation in the LHC, fortunately without success. International, that was a case where we were talking about national collaborations. International collaborations are that much harder. We've seen an example of this recently. There's a thermonuclear power laboratory, a very large project called ITER, International Thermonuclear Experimental Reactor. And the project was almost canceled because of a conflict whether it would be located in France or in Japan. And this may be the greatest obstacle to getting the thing built. But there are other obstacles. Science funding has generally decreased, not just building accelerators. For example, the National Science Foundation, a decade ago, granted a third of all grant proposals for research in science of all kinds. And now they grant only a little over 20% of those grant proposals. But the trouble is, as you cut down funding for science, you can't really reduce the funding for an accelerator. I mean, it doesn't work to build half an accelerator. The particles have to go all the way around. And it also doesn't help to build little accelerators because they're cheaper, because that would only give you things you already knew about. So there's no alternative to spending a lot of money if you want to advance our knowledge of nature at its deepest level. And this has led, unfortunately, to a degree of competition within the scientific community. There are scientists who don't work in elementary particle physics and who feel that the money being spent on expensive things like accelerators would be much better spent in other fields of science, as, for example, their own fields. And in particular, one of the things that hurt the SSC effort was the opposition of a solid-state physicist, a physicist who studies the properties of solids, who at that time was president-elect of the American Physical Society and therefore had a degree of influence he wouldn't otherwise have had. In making the argument for this kind of spending on big science, we're hampered by the fact that in the short run, we can't point to practical technologies that are going to come out of the discoveries we make. Elementary particle physics will not, in a foreseeable way, produce useful things like lasers or transistors, which are the product of research, for example, in the physics of the solid state. So we have to answer, why should society provide funds for these big projects, big accelerators? I think the answer has to be, and this is certainly the answer for me, a vision of the way the world is ordered. The properties of ordinary matter, the things we're made of, the things we use in our everyday life, are what they are because of the principles governing electrons and atomic nuclei and light and other kinds of electromagnetism and their interactions with each other. And we now know that those properties of atomic nuclei and electrons and so on are what they are because of the principles of the Standard Model, from which they can be derived. Where do the principles of the Standard Model come from? And how do we join that with other things that are not contained within the Standard Model, like gravity? Well, we don't know. And we want to make the next step toward a really unified view of nature. And it's a tragedy to imagine that this is going to come to an end in our own time. Not everyone feels that this kind of fundamental science is of importance. I remember I was on a radio show at the time we were arguing over the super collider, and there was a congressman took the opposite view, and he said he's not against science. He's not even necessarily against big science. He just thinks we have to set priorities. I said, well, I quite agree. Now, experiments at the super collider, the SSC, are going to help us discover the laws of nature, the principles governing everything. Wouldn't you think that would earn a high priority? I remember precisely what he said, word for word, because it was just one word. He said, no. What can you do? How do you make a case for someone who doesn't already feel the importance of what you're doing? Well, I think the least important argument we use, or we do use it because we use any argument we can think of, the least important argument is the technological spin-off. In a sense, big science is the technological substitute for war. Just as war pushes technology and develops things which are useful even in times of peace, like microwave ovens, which came out of the radar technology of World War II. In the same way, going beyond what we already know with experiments in fundamental physics pushes technology. One example, when physicists first started to try to accelerate electrons around in rings, they found, as could be understood theoretically, that a lot of the energy of the electrons was being drained off in a kind of radiation that was produced when electrons go round in circles, called synchrotron radiation. This was a nuisance for high-energy physics because it drained energy away from the accelerated electrons. But the synchrotron radiation itself turned out to be very important for studying the properties of materials. And it's a sort of nice twist that when Berkeley lost the Bevatron that I mentioned earlier, what it has now as a substitute is an accelerator that is designed to produce synchrotron radiation for practical purposes of studying materials. Another example of technological spin-off is the World Wide Web, which we all use, but it was invented by physicists at CERN as a means of sharing data that was coming out of experiments in elementary particle physics. We should also not, but although we talk about these spin-offs, this I don't think is anywhere near the most important thing. More important is the long run. Discoveries in fundamental science change the way we live, but it doesn't happen immediately. And to take an example, a little before the end of the 19th century, J.J. Thomson in Cambridge was making fundamental studies of the way electricity flows. And in the course of these studies, he discovered what was the first discovered elementary particle, the electron. And a huge electronics industry could not exist without the knowledge of the existence of this particle, which carries electric currents in all ordinary electric circuits. If J.J. Thomson in 1897 had been directed to work on practical problems, problems of immediate technological importance, he would have developed a better steam boiler. But he would not have discovered the electron. I think another important, and this is less rarely recognized, spin-off from high-energy physics is that it has a tremendous intellectual attraction. And I see this with students coming into my university. Many of them are motivated to go into science because of the challenge of discovering fundamental facts about the way the world is ordered. And many of them become scientists who do things of great practical importance. The society that decides that it will only support applied science and not waste money on pure science is likely to be a society that will wind up with neither. In the long run, though, I think perhaps the greatest contribution of fundamental physics, which necessarily is big science now, is as a contribution to our culture. I recently read a remark by Lytton Strachey, who you may know about as the author of Eminent Victorians. His remark was that the modern world began on July 15th, 1662, which was the date of the formation of the Royal Society, England's great Academy of Sciences. And in particular, the expansion of the scientific understanding that the world is governed by impersonal mathematical laws has left much less room for religious fanaticism. And I think it's not an accident that that countries, places like Europe, where the scientific revolution began, and countries like the United States and Japan that have embraced modern science, are the countries where religious fanaticism has greatly diminished, whereas in other parts of the world, it continues and continues to have its baleful effects. Now, I've been talking about physics because that's what I do and that's what I know best. There are examples of big science now increasingly also in biology, genome projects, and in geology, drilling down to the mantle of the Earth. I'm not going to talk about them because I don't know much about them, but I think probably very similar things could be said about them. The one other area where I do work is astronomy, and in particular cosmology. And by the way, I don't remember what time I started. There's 1:30? Okay. All right, fine. Then I probably have enough time. I can speak faster and faster. Astronomy has had a very different history from physics, although it is wound up in much the same situation. Astronomy was supported by government as big science from very early times. And that's because, unlike physics until recently, astronomy was useful. Astronomy was useful in the ancient world for making calendars, for telling time, for direction finding, for navigation. And for those who believed in astrology, it was important for predicting the future. And all of those led to government supports. When the Kingdom of Egypt, the Hellenistic Kingdom of Egypt, was founded as a fragment of Alexander the Great's empire after his death, the first kings of Hellenistic Egypt founded a scientific institute in Alexandria called the Museum. It was called the Museum because it was dedicated to the 9 muses. And one of the muses really took over from her sisters. It was the muse Urania, the muse of astronomy. And at this laboratory, well, I should call it perhaps an institute. At this institute, astronomers like Aristarchus and Eratosthenes worked, whom between them measured the size of the sun, the moon, and the earth, and the distance of the sun and moon from the earth. Spectacular achievement of ancient science. And this government support on a large scale of research in astronomy continued. Caliph al-Mamun founded the House of Wisdom in Baghdad. Frederick II of Denmark gave a very large grant to a nobleman, Tycho Brahe, to build an observatory, Uraniborg, on an island off the coast of Denmark. In more recent times, we have the Greenwich Observatory in England and the US Naval Observatory in America doing practical astronomy for navigation and timekeeping, and also doing fundamental research. In the 19th century, you have rich people, amateurs who get into the business and do research themselves. For instance, the 3rd Earl of Ross, in his home observatory, built the largest telescope in the world at the time, he called it Leviathan, and used it to, for example, to discover the fact that nebulae, what we now know of as galaxies, have spiral arms. And rich men in America who were not themselves amateur astronomers nevertheless began to build observatories and telescopes in order to gain respectability. And there are people with names like Yerkes, who was involved in the Chicago streetcar business where he needed respectability, and Lick and Hooker, and then more recently, Keck and Hobby. But now, astronomy is facing tasks that are way beyond the resources of private individuals and that strain the resources of government. You have to get observatories above the Earth's atmosphere. And this is not only because the Earth's atmosphere blurs images, but also because it blocks radiation of various wavelengths, like X-rays and infrared radiation, which are emitted by astronomical objects and which we need to study. And we can only do it by getting outside the atmosphere. There have been a number of these extraterrestrial observatories that have made this a golden age of cosmology in particular. For example, the Hubble Space Telescope not only makes those beautiful pictures of nebulae and planets that you may have seen, but together with a bunch of ground-based observatories, has discovered that the expansion of the universe, which had been thought to be must be slowing down because matter is attracting itself gravitationally and would tend to hold back an expansion, the expansion instead is speeding up because of some kind of mysterious dark energy that pervades all space that we don't yet understand. Another satellite that's less well known but equally exciting, called WMAP, Wilkinson Microwave Anisotropy Probe, is sitting out not just in low Earth orbit like Hubble, but 1 million miles from Earth. It's actually in orbit around the sun rather than around the Earth. And it's making exquisite measurements of the microwave radiation left over from a time when the universe was, well, when the Big Bang was 380,000 years old. And we using measurements of this radiation, we can infer that the Big Bang is 13.72 billion years old, and actually say this with a straight face. Well, I mean, the uncertainty is like 0.0 a few. And it also has allowed us to measure the abundances of various constituents of the universe, like ordinary matter, which is about 4%, the dark matter, which is about 24%, and everything else is this mysterious dark energy. So this has been a tremendously exciting time. In fact, cosmology has lately had some of the excitement that elementary particle physics used to have, and may have again when the Large Hadron Collider begins to make its discoveries. But it's awfully expensive, so it runs into the same problem as building accelerators, and it runs into another problem which is peculiar to astronomy, and that is that extraterrestrial observatories are funded by the same government agency that funds something entirely different, manned spaceflight. And manned spaceflight gets much more money than science does at NASA. In fact, let me be perfectly clear. The manned spaceflight program, although often sold as a scientific research program, is nothing of the sort. People, all of the great observatories in space that have made this such a wonderful time for astronomy and cosmology are unmanned. Human beings really play no role in space in this. It's all done by human beings on the ground in radio links to their extraterrestrial experiments. But science is receiving much less funding, and the funding is decreasing. The successor to the Hubble Space Telescope is another space telescope called the James Webb Space Telescope, which will specialize in infrared observations, which is necessary because when you look at something from very, very far away, because of the expansion of the universe, the light is shifted toward the red end of the spectrum. And you have to be able to study things at infrared wavelengths, which don't penetrate the Earth's atmosphere. This telescope is is intended to go out 1 million miles from Earth in the general neighborhood of where the WMAP, did I say accelerator? Observatory was located. It is continuing to be funded, but at a level which will guarantee it will never fly. And another program was identified last year by the astronomical community working through a committee of the National Academy of Sciences. They were asked to prioritize research in astronomy, and in particular, they identified what they regarded as the #1 priority, an infrared observatory called WFIRST, I don't remember what it stands for, which is intended, among other things, to probe the dark energy, which is causing the expansion of the universe to accelerate. In the budget for NASA, there is no funds at all for that, the top priority of the astronomers. And yet, manned spaceflight, fortunately somewhat diminished now, continues as the major part of NASA's budget. I speak of this with some feeling. In fact, I have to think I'm probably getting to be a bore on this subject, because when the Super Collider was canceled, it was in competition with the International Space Station. The International Space Station was sold as a scientific research laboratory. It has produced nothing of scientific value. It is true that there is, just in the latest Endeavour launch, there is a laboratory going up to the International Space Station to study cosmic rays, not for discovering new kinds of particles, but to study cosmic rays for their own sake. It will do, for the first time, real science on board the International Space Station. So you might say that's a counterexample to what I was saying. But in fact, it could much more cheaply have been built to be launched by an unmanned rocket And its operation, whether on an unmanned observatory or on the International Space Station, will not involve human beings in any way. I'm told that there's a switch which the astronauts can turn on, but that's it as far as their participation. Now, unfortunately, Congress was very confused about this issue of the scientific importance. I remember once at a congressional hearing, a congressman said he could understand how the International Space Station would help us to learn about the universe, but he couldn't understand that about the SSC. And I had already testified, so I couldn't say anything, so I just sat there and cried. President Clinton felt that he could only give active support to one Texas project. The International Space Station was seen as a Texas project because it was governed from Houston, the Manned Spaceflight Center. And he decided he would support the International Space Station. And Congress was very glad to go along. In fact, one of the things that gave the International Space Station an advantage over the SSC is that it was much more expensive. It has cost about $100 billion as compared to what the SSC would have cost, which was about $10 billion. And that $100 billion was cleverly spread by NASA in contracts over the whole country, so that there were congressmen from many districts and senators from practically every state who were active supporters of the International Space Station. Well, the big science in the form I've been describing it runs into competition not only from manned spaceflight, of course, or from other branches of science like solid-state physics or medicine or geology, but it runs into competition with lots of the other things our society needs government to adequately support. We need education to be supported at a level so that a teaching career will be attractive to the best graduates of our colleges, as it now isn't. Our passenger rail infrastructure and our internet access structure, even our bridges, are at a state which look very poor compared to their counterparts in Europe or East Asia. Our patent office is so undermanned it takes years to get a patent application approved. Our judiciary is so undermanned that it takes years to get a civil action heard. Our prisons are so undermanned that being incarcerated, the Supreme Court recently decided, in some states amounts to cruel and unusual punishment. Violation of, what is it, the Eighth Amendment. Our ports are insecure to terrorists, and many Americans go without adequate health care. These are all things that require government support. Now, for each one of the things I mentioned, there are plenty of advocates, just like I'm an advocate for big science. But we tend to get in each other's way. We tend to conflict with each other. I ran into an example of this, I'm almost finished, a little while ago, some years ago in Texas. I found myself sitting at dinner with a member of the Appropriations Committee of the Texas House. And she learned I was a professor at the University of Texas, and she began to tell me how she was enthusiastically supporting more funding for higher education. And of course, this wasn't something I minded hearing. And then I stupidly asked her, I told her, I'm so glad to hear this. What are you planning as the revenue source to support this? And she blinked at me and she said, oh no, I'm not planning to raise taxes. We're going to take the money from health care. This is not what we need. What we need is for those of us who care about government support for all the things our society needs, to unite, to help shift the balance of our economy more away from private goods in the direction of public goods, where the real needs of our society are. The real needs of our society are not for more consumer electronics, but for education, healthcare, scientific research, and so on. And this means higher taxes, which is a hard sell in a time when an anti-tax mania has afflicted the American public. But it's only in this way that we can get adequate funding for all the things that our society really needs, for education, for healthcare, for infrastructure, and all the others, and also for science of all sizes. Thank you.